voter's ballot we're voting. So you can't do this. You could try to put random identifiers, pseudo-random identifiers, generate them at random, generate them cryptographically, I don't care, onto the ballots, and then record those on the electronic record. But how do you as a voter know that the code that's on your ballot actually contains no information about who you are or what the sequence number does? If it's generated randomly or pseudo-randomly, right, it's a theorem that you can't tell that apart from a well-encrypted value. You also don't know whether someone whether or not someone wrote down the fact that the top ballot in the pile has serial number 325631 or whatever it is. So voters in this kind of system can't have confidence in the privacy of their ballot. And the voters' confidence in the privacy is what lets them resist vote buying and coercion. So we have a problem if we are going to audit by ballots with the secret ballot. All right. So now I want to tell you how to solve this problem. And this is a result that Joe Calandrino, Alex Halderman, and I published this year. A method called machine-assisted auditing. And the idea is this. The first step is we're going to check the electronic records against the paper records by using a recount machine. We're going to use a machine to do the recount. And of course, we don't trust that machine. So the second step is going to be that we're going to audit the machine by doing a random manual recount of what the machine did. All right. So it works kind of like this. The first thing we do is we take the paper ballots and we run them through this machine, which scans them and counts them and produces two things. First of all, on the bottom, it produces an electronic record of all of the ballots it scanned and what it says was on those ballots in order with serial numbers. It also, as a side effect, prints serial numbers on the ballot, on the paper ballots. Now, this is not a voter privacy problem because remember, before all of this stuff happens at the end of the day in Election Day, all of the ballots were thrown into a single ballot box. They all got mingled together and shuffled around, and then maybe you shook up the box, maybe not, but anyway, the ballots are all mingled together. And then the voters went home. So these serial numbers don't record the order in which the ballots were cast. They just record the order in which the sheets happened to be stacked up in the sheet-fed scanner when you did this recount. Right. Now we compare the tally, the electronic tally that the voting machine kept on Election Day with the result of this machine recount and make sure that the electronic records match. Okay. So now, if this machine is honest, then this audit is good, and it will tell us whether there's a discrepancy between the paper and electronic ballots. But we need to audit the machine. The way we do this is like this. We audit the recount machine by selecting some of the ballots at random for human inspection. So we do some random process, and we produce, in this case, the decision that we're going to audit ballot number 321 and ballot number 716, which are allegedly cast for Bob and Alice, respectively. So we go into the pile of paper ballots, we pull out those two, we look at them manually, and we compare to the electronic record for those ballots, and we make sure that it's equal. This gives us some kind of check, which is valid to some statistical level on the accuracy of this recount machine, right? And I hope it, and it should be clear that if we do this in enough places, that we can get enough confidence in the recount machines that we know that the result is good. And in fact, I'll assert to you that there's a theorem that says that that's the case. The result of this is that we can use a machine without having to trust it. And this, it turns out, is as efficient as ballot-based auditing. The number of ballots that you have to touch by hand is equal to the number that you would audit if you were using ballot-based auditing. And it also protects the secret ballot because of the intermediate step. All right, so how much good does this do? Here's some data based on data from the 2006 Virginia U.S. Senate race between Webb and Allen. If you did, this is a very close race, 0.3% margin of victory, and we want 95% statistical confidence that we'd catch a discrepancy between paper and electronic. As an aside, Virginia didn't actually use voter-verified paper ballots in this election, but we're pretending that they did and using the data to do this analysis. All right, so if you did precinct-based scanning, you'd have to count about half the ballots, about 1.1 million, by hand in about 1,200 precincts. With machine-assisted auditing, we can get down to about 2,300 ballots that are examined by hand in about 1,300 precincts, so about 1.7 or 8 ballots per precinct examined by hand with the same level of confidence. But it turns out we can do even better by thinking more carefully about what it is that we're trying to establish. So our original goal was to reject the hypothesis that more than 5% of the ballots differed. But it turns out that if we think more carefully, all we need to do is reject the hypothesis that more than 5% or more of the ballots are marked electronically for Alice, but on paper for Bob. That's the scenario we worry about, the scenario where a paper recount would swing toward Bob. If Alice should have won by more than 10%, we don't care. But if we're looking for this hypothesis, this tells us something interesting. If we're looking for ballots that were marked electronically for Alice but on paper for Bob, it's immediately obvious we don't need to look at all at any ballots that are marked electronically for Bob, because they can't possibly fall into this category. So 45% of the electronic ballots we can just set aside and not look at all. We only need to audit the ballots that are marked for Alice. Now, this is a two-candidate race where there's no write-ins, there's no undervotes or any of that, but it turns out that you can work out an algorithm, and we did, that is more general. In general, the probability of auditing a ballot can depend on how that ballot is marked. The intuition being that ballots that are marked for winning candidates get more attention, ballots that are marked allegedly for losing candidates get less attention. And the full algorithm accounts for multi-candidate races, multi-seat races, undervotes and overvotes, write-ins, and all that stuff. And you can prove that it is as good as the previous auditing method. Now, if you do this content-sensitive recounting in the Webb-Allen race, you get about another factor of 2 saving, so that you now are hand counting about 1,100 ballots statewide, about a factor of 1,000 better than the precinct-based method that is what's actually used everywhere, as far as we can tell. And the number of precincts is lower. So by using this content-based method, you can actually need to touch fewer precincts at all, and also touch many fewer ballots than with other methods. All right. So I hope I've convinced you at least a little bit that if you use new electronic technologies correctly and creatively, we can make voting cheaper, faster, and more reliable than a paper-based system. You can do better than paper-based. Shouldn't be our goal to get back to where we were before these computers came along, but our goal should be to do better. Where it's possible, we want to design the technology so we don't have to trust it. We want to have the paper trail on the side of an electronic counting system. If we're using machines in recounting, we want to check up on them with manual checking. Research, there's a lot of interesting research going on in this area. There are now 3 conferences or workshops annually on electronic voting, and some really interesting ideas about how to do better. And we're making really rapid progress on some of the problems we need to solve. On other problems, not so much. But in practice, we have a long way to go. There's a lot we don't understand about what to do. And even if we, the research community, understood exactly what to do or thought we did, there's a long road to get it deployed and all the things we learn along the way. And there's a long road to convince public officials to have trust in us and our technologies to change things. Thanks. I'd be happy to take any questions. We have, I think, just a
Please remember to turn on your microphone.
Yes. Yeah, I was 2 questions. One, how much is the cost of each machine? And the second one is, when you are making the counting, why don't you generate a stack of papers for each count, just saying not the name, but what it's going to be randomly, and when you feed it through to check the machine afterward, just to make sure that it works fine.
So how much do the machines cost? The DRE-type electronic voting machines cost a few $1,000s typically. The sort of sheet-fed scanner that I talked about is probably also $1,000 or so for equipment. The cost of the machines for casting the votes is probably the biggest factor in practice, because you need more of them. You need one vote casting machine for every couple hundred voters probably. Whereas the recount machines, you might need only a few hundred or 1,000 across the whole state of Virginia, for example. The other question is, why don't you sort of randomly select some papers to audit? There actually are alternative algorithms that are sort of cut and choose algorithms where you ask the voting official to divide the ballots into papers into 2 piles, and then you choose which one you're going to audit. If you're going to divide the ballots into piles based on how they were cast, you again have this problem of either you use a machine to do that, and you shouldn't necessarily trust that the machine got it right, or you do it by hand, which is equivalent to doing a count.
I mean, you have